Okay. So this is the standard disclaimer that we have. There's nothing much in this talk that's going to be a surprise to most of you. So yada, yada, yada. Agenda. So there are three parts to this talk. So in the first part, we'll talk about the vNetwork distributed switch. We'll introduce some concepts around the vNetwork distributed switch. And we'll also look at what is new in the 4.1 version of VMware VDS. In the second part, we'll introduce some VDS management tools, and we would be doing that. And in the third part, I'll be back for some notes on troubleshooting. So there's a lot more detail on troubleshooting in the slides, so feel free to look at it offline. All right, so the first section. So vNetwork distributed switch concepts. Right, what have we tried to do here? So first, in the ESX 3.0 timeframe, we decided to enable the consolidation use case. For that, we went out and built this simple switch that actually provides networking for virtual machines so as to enable consolidation. So this simple switch is also called the vNetwork standard switch. The thing about the simple switch is it needed to be managed on each host individually. And with going into DRS and all these cluster concepts, that was not a scalable way of managing a fairly large piece of infrastructure. So what we did with vSphere 4.0 is introduce the vNetwork distributed switch. In the vNetwork distributed switch, we have a management plane that is central, that exists in either vCenter server or as an extension to vCenter server, and a data plane that is the proxy switch that exists on each of these ESX servers. Also, as part of the vNetwork distributed switch, we built certain standard data path APIs that enabled extensibility with third-party switch platform vendors like Cisco's N1K. This talk primarily covers VDS concepts and VMware VDS. There are other sessions that cover the N1K product in greater detail. So what are the components of the vNetwork distributed switch? So there is a central management plane. This central management plane exists as a module within the vCenter server for the case of the VMware VDS. And there's an external management plane, which is called the supervisor module, which can be a virtual appliance or a physical box, depending on what you buy from the N1K family of products. And that is basically a vCenter extension. Now, every time you add a host to VDS, there is a piece of a module that's loaded on each of these hosts. This module is called the proxy switch. This is a central concept in where switching actually happens. So you control your configuration through the management plane, but you actually switch your packets out through the data plane, and the data plane exists on each of the ESX hosts. So there is no operational dependence in terms of like being able to switch VM packets out in the case of both the Nexus and the VMware VDS. Let's take another look at the port group. And so many of you are familiar with the vSwitch port group, which is called the standard switch port group. So what we've done with the vNetwork distributed switch is evolve the port group as a central management concept across hosts. So what does the port group do? It provides the central management abstraction to manage your network configuration. So if you wanted to set your VLAN, you want to set your teaming, you want to set your PVLAN configuration, this is the object you need to muck around with. It is also the object to which virtual adapters connect to. So if you want your VM to get networking in the VDS world, you would connect your VM to a distributed port group. The distributed port group spans the entire span of a vNetwork distributed switch. So if a host is a member of the VDS, it can see the distributed virtual port group. The distributed virtual port group also contains these ports. They're called distributed virtual ports. These are the actual objects through which I/O gets passed. DV port groups, by default, inherit configuration from the DV port group that it's a part of. There are advanced workflows through which you can actually override configuration on a per DV port basis, and please refer to the product documentation to figure out how to do that part. So another concept that the vNetwork distributed port group brings to life is the notion of binding. So what is binding? The act of assigning a particular instance of a DV port to a virtual adapter is called binding. There are three types of bindings that the distributed virtual port group supports today. So the first one is static binding. This is the default configuration, and this is recommended for performance and scalability reasons as well. In this case, the port is bound to the vNic whenever you connect the VM to the distributed virtual port group. This is the most stable configuration, and it gives you the look and feel of a physical switch, as in you connect a wire into a physical switch port, and it stays connected for as long as the wire is inside the hole. The second aspect of the second form of port binding is dynamic port binding. You would use this when you have a certain number of ports that are present in a DV port group, but you want to connect more VMs than the number of ports within that port group. But note that at any given point in time, you can only send I/O through as many ports as there are in the DV port group. So this works for an over-provisioned use case, but it has the performance implication that the port is bound when the VM is powered on, and it's unbound when the VM is powered off. So this would obviously operate slower than in the case of the static distributed virtual port group. The third type of port binding is ephemeral port binding. This is the most transient form of port binding. In this mechanism of port binding, every time a VM is powered on, a DV port is instantiated within that DV port group and bound to that virtual machine. And every time the VM is powered off, it's unbound and destroyed. So you'd want to use this when you actually have a very large number of VMs and you don't really care about like the nature of port to vNic binding or history of the port itself. And as another note, the maximum number of ports attribute of a port group is not enforced in the case of ephemeral port groups. Again, if you had one takeaway from this slide, our recommendation would be to use static binding. This is because it's the most scalable and best performant port group type out there. So the second concept that we would like to introduce about the vNetwork distributed switch is around its state management and how that functions with regards to mobility, FT, and high availability scenarios. So state. So where is state persisted? There is a centralized piece of state that exists in the management plane that actually maintains all the configuration of the VDS. This central state is persisted in the VC database. There's also distributed state that is needed for operational purposes, and that is what the proxy switch on the host uses to make switching decisions. That exists on the host as part of the local cache. So the vCenter server also serves an additional role in that it is what ensures that the central management state persisted in the vCenter database is in sync with the host state. So if the host state diverges, the vCenter server just clobbers the state on the host. So you have the authoritative state in the management DB. So again, highlighting one other point, the proxy switch or the switch on each of the ESX hosts operates off the local cache. So there is no operational dependence on vCenter server. So if you have a split brain problem, you're not able to talk to your vCenter, your VMs on the ESX host will just do fine. Also note that the local cache is a binary file, so please don't try and edit it or something like that. That gets us into trouble. Okay, so let's take a look at vMotion. So how does vMotion work today? Without VDS, we used to just have to migrate the VM state. Now, once you have VDS, there is also state associated with the port. So as part of the VM checkpoint state, we also checkpoint the DV port state. And as part of the migrate, the packets are encapsulated and sent across to the destination, and the checkpoint state is restored, and the DV port state is restored back on the destination. So all this seems like there has been no change in the port state regardless of where it's running. So this piece of stateful migration is fairly central to the concept of the vNetwork distributed switch. How does HA work? So HA works by making use of the shared data store. So what happens in the case of HA is that periodically the in-memory state is persisted to the shared data store. And in case there is a failure, the destination host knows exactly where the shared data store is because the VM existed there and can read the state from that shared data store. So this is how the port state actually migrates to the failed over host. FT. So in case of FT, what we do is that we do these periodic checkpoints as part of migrating the VM state. And along with that, we have added hooks in the VDS framework to also be able to checkpoint the port state. So periodically, the port state is synced from the primary to the secondary. So when the primary goes down, there is a seamless transition to the secondary. So there is no reboot required, and it's transparent failover, and the guest doesn't even know that an FT failover has occurred. So to conclude this section, I'd like to point out some key takeaways. So the first concept that VDS introduces is a centralized management plane. This provides you with a single pane of glass for you to be able to manage your entire infrastructure, and given that it's fairly homogeneous, it makes it very easy to do so. There's a traceable VM to port mapping. So this is something that a lot of network admins out there are very familiar with, and it's something that there are a lot of tools built around. So this sort of makes it more fit into existing physical port to server binding concepts. There's stateful VM and port migration. So the port state migrates as part of vMotion and all these other mobility events. And for fault tolerance and high availability, there is no operational dependence on vCenter. So if vCenter is down or you can't ping your vCenter from your host, there should be no problem. HA and FT would just work fine regardless of VDS being present in the scenario. So vCenter is only required to manage your configuration. So if you want to change the VLAN on which your port is sitting, then you use vCenter. But once you've changed your VLAN, you don't have any operational dependence on it anymore. So let's take a look at what we introduced in the vNetwork distributed switch 4.1. So what's new? So network I/O control. This is a central feature that enables managing the infrastructure at scale. Some of you heard Steve talk about it in the keynote as well yesterday. There's load-based teaming. It looks to solve the problem of using teaming as a way of adaptively rebalancing your traffic, so you don't have to worry about like what is my active configuration, what is my passive configuration. Just trust the infrastructure to figure it out for you. And the last thing is scalability. So one of the main focuses of the 4.1 vSphere release itself has been around scalability, to be able to create this giant bubble. And as part of that effort, we've also bumped up the limits on the vNetwork distributed switch for VMware. Okay, before I dive into network I/O control and how that works, I'd like to actually spend a minute on the emergence of the 10 gigabit interfaces and I/O convergence. So if there was one thing that you wanted to leave this conversation with, I'd recommend that it be start thinking about converged networks and how that's going to simplify your networking. So on the figure to the figure on the left, this is what we had, and this is what a lot of us have at this point, because 10 gig is still expensive. So in this case, what we have is we have multiple physical NICs that are coming into your ESX server. They're all gigabit links, and they're teamed according to iSCSI, FT, vMotion, NFS, and all these traffic types. So these dedicated NICs provide one big advantage in that it also provides bandwidth assurance. So since your iSCSI has 2 physical NICs in an active passive configuration, whatever storage traffic is going out is not going to interfere with the vMotion traffic. So this is going to be this is a good way to solve the noisy neighbor problem, but this is not a great way to solve underutilization of bandwidth because you're already statically partitioning your physical network resources. So what 10 GigE has come in and is trying to tell us is that, hey, let's try and simplify your physical network by converging it into a pair of uplinks. And the pipe is fat enough that it can handle a lot of your traffic types. So you're going to reduce your cabling complexity, you're going to reduce the number of switches you need in the way, and all these other issues as well. But the other side effect of bringing the 10 GigE into your environment is that you have no idea about what traffic types are going to compete for that 10 gigabit E link. So to solve this, one of the things that we've tried to do is to introduce the concept of network I/O control. So what are the other goals of network I/O control? So the first one is traffic isolation, which I just spoke about at length. The second one is to be able to flexibly partition your 10 GigE. So supposing you have an environment in which your virtual machine traffic requires higher priority than your NFS traffic, you're free to do so, as in there are certain control knobs that you need to use, but it's configurable. The second aspect is that there's traffic prioritization. So you can actually assign like knobs like shares to your traffic types, and this helps you prioritize your traffic. There's predictability in performance, which is very important, as in if you want to enable your infrastructure to move to the 10 gigabit network, then you need some predictability in terms of performance. And this is also an enabler for converging networks where you want your storage and your network traffic to share the same pipe. So network I/O control. So in 4.1, we introduced the notion of traffic types. So there are 6 traffic types that the infrastructure fundamentally recognizes, from virtual machine traffic to ESX server management traffic. There are 3 concepts that we also introduce as part of the network I/O control feature. The first one is the network resource pool. A network resource pool concept is very similar to what you already have in the DRS-based environments for CPU and memory. It enables you to guarantee certain service level guarantees for network traffic. There are 2 knobs that network resource pools provide you with. The first one is limits. It's specified as an absolute number in megabits per second, and it's enforced per proxy switch. The second one is shares. It's very similar to the memory and CPU configuration knob. It's specified in abstract units from 1 to 100. And shares inherently are work conserving. So if you have assigned 100 shares to NFS and there's no NFS traffic, then we'll just redistribute the shares amongst the other traffic types. So it's not a hard limit like reservation is. So here is the architecture diagram of network I/O control. So I'd like to walk you all through 3 specific aspects. The first thing is teaming. So teaming is the first line of defense. So teaming decides which uplinks get used by which traffic originating from which port group. Once teaming has been decided, the shaper module comes in the way. And shaper is where limits are enforced. And you should note that limits are enforced per team. So it's not at an individual leg of the team. And the third concept is the scheduler. That's where shares are enforced. So each packet from a particular traffic type is assigned a priority, and the scheduler is the thing that interprets the priority and then assigns and then schedules the packet on the uplink. So today we support only transmit-based prioritization. We are talking with physical switch partners to also try and see something about receive side, but this feature only enables transmit side. So also it's worth noting that network I/O control is only available with VDS. So just to demonstrate the usefulness of this feature, I'd like to dive a little more in depth analysis of a particular case study. So this is sort of our setup. We have two ESX hosts, and each ESX host has access to one active 10 gigabit physical network interface. And there is vMotion traffic in the background, as in we have these VMs that are just bouncing up and down from ESX host 1 to ESX host 2. There's FT traffic, as in some VMs are also FT enabled. There's NFS traffic, as in some VMs have their base disk on an NFS data store. And there's vMotion traffic. So the following illustrates what happens in this environment if you didn't have NetIO control enabled. So on the left, we have a SpecWeb benchmark running in the guest, and on the right, we have IR meter running within the guest. So you notice that once we start background vMotions, there's a 67% drop in user sessions for the SpecWeb benchmark support. And there's a latency increase of 13 times for the NFS-IO latency. So what this demonstrates is that in a scenario when you don't use network I/O control, your traffic is prone to bursts, being affected by bursts, particularly of the nature of things like vMotion traffic. So now we enabled NetIO control on the same setup. We enabled FT traffic as the highest priority, and then NFS and VM traffic having higher priority over vMotion. And the diagram on the left also gives you insight into specific shares and limit settings that we had. Notice that once I/O control is enabled, you can't really make out when the vMotion, the background vMotion started for both your SpecWeb and your NFS benchmarks. So what this demonstrates is that with NetIO control enabled, you can sort of isolate your application's performance from background infrastructure noise or other noisy neighbor VM problems. So this is another graphic representation of the same. So notice on the left that even though the vMotion traffic spiking up has starved the NFS, FT, and VM traffic. And notice on the right that the vMotion traffic doesn't spike as much, leaving the NFS, FT, and VM traffic with a reasonable amount of bandwidth. The throughput is comparable as well. So this is work conserving. So another concept that we introduced in 4.1 is load-based teaming. So what we are saying here is that teaming is a good way to avoid congestion because it's the first line of defense. As in, if you have two virtual machines that are generating a lot of I/O and you're using source MAC or port-based hashing, it might be that the I/O ends up on the same uplink. And that might not be good for the performance of either of the VMs. So what load-based teaming is trying to do is say that you set the default policy of your port group to be load-based teaming, and the infrastructure would ensure that the traffic gets prioritized on the right legs. So what this diagram also illustrates is a small example. So on the left, you have traffic coming up as an initial configuration, iSCSI, vMotion, and FT traffic. And you notice that the vMotion and the iSCSI traffic got hashed to the same physical NIC because they have a port number that actually hashes to the same physical NIC. Then after 30 seconds, if the infrastructure detects saturation, which in this case is true, we would end up rebalancing the traffic across different legs of the team, ensuring that there is more fair distribution of traffic. This way, you can ensure that the throughput is increased. So it's also a recommendation that you use load-based teaming in conjunction with network I/O control. Scalability. So one of the goals of VMware or vSphere as such is to enable users to manage their infrastructure at scale. So this has been a focus of the 4.1 effort, and we can now do 8 vMotions at a time. The number of VMs supported in the infrastructure has increased. So in keeping with that theme, we've also bumped up the vSphere limits for distributed across the vNetwork distributed switch. In specific, I would like to call out 2 numbers. The number of ports per vCenter in 4.0 was 6,000. In 4.1, it's now 20,000. And the number of static port groups per vCenter in 4.0 was 512. It is now 5,000. And I'd like to emphasize again, use static distributed port groups for better performance, particularly if you're operating at a large-scale environment. So with that, I'd like to hand on to Wei, who's going to talk to you about the VDS management tools.
Okay, thanks, Amar. Okay, I'm Wei, and I come from VMware Beijing office. So, how you doing? And okay, let's start. I'll talk about the management tools. vSphere client, the console, SSH, logs, VCLI, VMA, ESX top, and CDP. So, vSphere client. Suppose all of you already have the knowledge of the vSphere client, so I'll go through this slides quickly. And this is the configuration interface for the vSwitch. So you could create and remove, change some properties of the vSwitch. And this is the physical leaks informations from the vSphere client. You could find out the type, the connection speed, the networking hint, and some other information from it. So, and this one is the configurations interface for the VDIs. So it's a little different than the normal vSwitch because VDS is different, right? And this is the new feature that is only for the VDIs. It is monitoring view. You could find out the real-time traffic in that monitoring view. So that's all for the vSphere client. And at the same time, vSphere also provides the service consoles for the command lines, configuration, and management. So I'd like to look, but in the 4.1, from the 4.1, VMware suggests you to transfer your ESX to ESXi to get more performance and more security. So I'd like to know how many of you use the service console for the configuration and troubleshooting. Could you raise your hand? Okay. So I think it's bad to you. But I have a good news and a bad news. The good news is ESXi still provides the SSH protocol support for troubleshooting. But the bad news is it is disabled by default. So you should, if you want to use it, you should enable it firstly. Yeah, I think it's a little difficult. So you need 4 steps. The step 1 is log in the console, and step 2 to select the troubleshooting options. Step 3 to enable the remote technical support, and wait to change to disable that. And the step 4 is to log in by your SSH client and run the ESS command. Yeah, I think it's quite complex. Right? So another very important information to help you do the troubleshooting is the logs. And in the Service Console, sometimes I always face a problem that it's difficult to find out where is the log. So in the ESXi, it integrates the log into the console screen. You could select the view system logs and select the message item. You will get the system logs. I think it is easier than the SSH. It only need 2 steps. Okay. And vSphere also provide the VCLI tools for you. And at the same time, vSphere also provide VMA tools. That is a VM with the vSphere client CLI pre-installed. So you could download it from this URL and power on. You need to install anything. You could use the VCLI. Okay. Sometimes you need to find out the real-time problem in your systems. vSphere provides the ESX top tools for you. ESX top is the real-time monitoring tools. It could monitor the CPU, the memory, and the networking. So you could press N to switch to the networking view and find out such as image interface and physical NIC, or some switch, or some the real-time traffic on it. So this is the SSH version. So for the remote version is the ESX top, which provided by the VMA. That's the similar output of the ESX top. And CTPC is the physical discovery protocol, which could help you to find out which physical switch and which port that your uplink connects to, such as this one. Could find out, okay, the device ID, the IP address, and some physical platform names. Okay, and the last one is the networking hints. It is the networking package observed in the uplink, so it will help you to do the troubleshooting. Okay, that's all of mine. Welcome, Amar, for the next. Okay.
I'd like to talk now about VDS troubleshooting. So I strongly believe to err is human, and to really mess it up requires networking. So it's like we'd go over a couple of common scenarios, but as always, there's a lot more documentation available offline, and support and folks are always ready to help you out. So the first part of troubleshooting a networking environment that's operating on virtual infrastructure is to try and break down the problem into layers. Right? So how do you troubleshoot this? So first, try and isolate the component that might be causing the issue. So we have the physical NIC, then we have the vNetwork distributed switch layer, or the virtual switch layer, depending on whichever SKU of networking you're operating under. Then you have virtual NICs, and then you have the physical network. So basically, any networking problem needs to be troubleshooted at like one of these 4 layers for you to be able to identify the problem. So a couple of tools that we have already out there that can be used for troubleshooting, which Wei went over, is the vSphere client, the command line utilities, the vSphere CLI, the RESX stop, and friends. And then there are, of course, third-party standard tools out there that help you with troubleshooting, like ping and traceroute, and then traffic sniffers. And lastly, if you really need it, logs are always available. So if you are comfortable parsing the logs, they always have a reasonable level of information. So one thing that we generally recommend in terms of how do you troubleshoot a problem is to try and sniff for it. Right, so you can sniff for a problem at 2 different layers. So the first thing is to sniff for it at the physical switch. So this is your standard network admin procedure. That is, you mirror a port, and then you attach a sniffer on the other end, and then you watch traffic going in and out of the switch. And that might give you insight into what might be the problems. So look in specific for lost packets, large number of packet retransmissions, and any anomalies reported by the protocol analyzers. So the second layer at which you can do sniffing is to enable a port group into promiscuous mode and install a sniffer within the application itself, and then you would be able to sniff for traffic that's coming in and out of the virtual switch itself. There is some documentation available in terms of knowledge base articles on how do you enable promiscuous mode and how do you actually get this setup working. I defer to that, the detailed resources available in order to help you guys out with this situation. All right. So the third aspect that is very useful when you're looking at a running system is to look at the CLI utilities. So there are 2 things that we'd like to point out here. The first one is the ESX stop and its remote cousin, which is the RESX stop, and the ESXCFG info, and the friend of the remote equivalent, which is the VICFG info. So the first thing would be to look for the particular interface that you're trying to troubleshoot. So in this case, let us assume we are trying to troubleshoot, say, FT traffic or VMotion traffic, and it's going out through this particular VM kernel interface, which is VMK TCP/IP, and provides you with some level of IP address information as well. So the second thing is to identify the real-time traffic that's associated with that interface. And if you're looking for static information, you look at the output of ESXCFG info, and you look for the same port that you've just seen through ESX stop. That would give you the port ID for the virtual NIC that you're interested in. It also gives you cumulative traffic information. So if you don't have a problem currently and you're seeing a problem in an intermediate fashion, then this would be able to record certain historical aspects in terms of say drop packets or any of these things that had occurred in the past, but you're not able to see it at that point in time. So we'd also like to cover a couple of scenarios. We've tried to identify 2 scenarios that are very common in terms of calls that we're getting for support, as well as things we're seeing on the forum. And it also covers a broad enough spectrum that it might be useful for other scenarios as well. So the first problem is none of my VMs have networking. That's a big problem, right? So you have to do something about it. So step 1 is to check inside the VM. So is the guest network interface up, and does it have an IP address? So some of this might seem basic. We're just trying to break down the problem into different steps. So use OS-specific utilities, and you can look for, in Windows, you look for network connections, ipconfig, and in Linux, you use something like ifconfig. To eliminate DHCP server-related issues, as in you're not getting some address correctly assigned, or just reducing the variability, we generally recommend that if you think you have guest-related issues, try and reassign it a static IP address. That way, you'll reduce the number of moving parts. So step 2 is to check what the vNic itself is connected to. Check the vNic is connected to the port group or the distributed port group that you really want it to be connected to. And also make sure that the connected box is checked. So if the VM is already powered on, it should say connected, and it should automatically be checked. And if you're going to power on the VM, then you make sure that the connected power on checkbox is checked. Also, you need to so once you've established that your vNic is connected to the right port group, then the next thing we recommend you to do is to try and talk to a VM on the same host that's also connected to the same port group. This eliminates issue. If you can do that, then you can narrow down the issue as something that's related to the physical NIC layer or on the physical side outside the ESX box. So if you've managed to actually be able to talk to a VM on on the same host that's connected to the same port group, then obviously you have a problem on the physical side. So check that the right uplinks are connected. You can use the vSphere client or ESXCFG or VICFG vSwitch to identify that. Check the RxTX counters for the physical NIC using ESXCFG info. I've tried to highlight the two particular fields of interest here. And also check that you're connected to the right physical switch and port. You can find that out by looking at the CDP info as vMotion or at network hint to be able to identify that. Okay, step 4 would be to check the VLAN configuration. Now there are 3 layers at which you can do your VLAN tagging. So the first one is at the physical switch. So in this case, the virtual side doesn't even know about VLANs, as in, so your port group is VLAN unaware, and so is your guest. So what happens is that the switch will encapsulate the packets as well as strip it on inbound traffic. So the second layer at which you could do VLAN tagging is at the virtual switch layer. So check that the physical port is in trunk mode. So the physical port that your uplink is connected to needs to be able to transmit traffic from the particular VLAN that you have enabled on your port group. So this is recommended. It's recommended that you move your access port into trunk mode and trunk the specific VLANs that are in use by your port groups. And the third thing, which is less common from our experience with the field, is to do virtual guest tagging. So in this, the guest tags the VLAN of the packets, and we don't tag the packets in either the virtual switch layer or the physical switch layer. So check that the physical ports are again in trunk mode, so it can actually let traffic from that particular VLAN through. And you also need to check that the port group VLAN is 4095. This means that we will not tag the VLAN on the virtual switch level. Okay, so that was about troubleshooting if no VMs have networking. So the second scenario we'd like to dive into is some of my VMs have networking and some don't. What do I do then? So the first step one is to pretty much do what you did in scenario 1, which is to round up the usual suspects. Right? Check the vNic on the VM and make sure it's connected to the right ports and the right switch, and your VLAN is configured fine. Step 2 is to make sure that the different NICs across your team are all connected to a physical switch that is configured with the same broadcast domain. So both your NICs need to be on the same broadcast domain, as one VM might decide to fail over, or multiple VMs can be using different legs of the team. Excuse me. Check the VLAN configuration of your environment again. This is different from verifying the validity of the tagging at the different layers of the stack. This is to make sure that all the access ports are configured identically in terms of VLAN configuration. And it's also recommended that you actually telnet into the switch and manually configure the switch port again to make sure that it's trunking the right VLANs. Step 4, this is a problem that we've been having recently, and we've had a lot of customer-related issues around, which is to make sure that the MTU is valid and it matches up across your entire physical domain. So what you want to do is you manually need to be able to verify the configuration of the MTU that's been set at the guest, at the virtual switch, and on the physical side. Once you've verified that, it's also recommended that you try using some tool like ping with a large packet size to verify you're able to ping outside from the guest. If you're not able to ping, that points to a fairly basic issue in your network connectivity, and that's why probably your VMs don't have networking. So additional considerations that we'd like to point out is that it's recommended that you disable STP on the access physical port, because this means that your physical port might not move into forwarding state immediately. So this might result in failure of networking after a vMotion or after a teaming failure. The second thing that we would like to make sure everyone is doing is to set notify switch property through the VI client to be true. What this does is sends a reverse ARP from the destination, so that way your physical switch can learn that a new MAC address has arrived on a host. This is very relevant for vMotion scenarios. So if you notice a loss in network connectivity after vMotion, then we recommend you take a look at this parameter. By default, it's set to true, so unless you explicitly disabled it, it should work fine. Some applications like IDS need promiscuous mode to be set on the port group. So if you notice that an application that you're running in a virtualized environment is not working correctly, then we recommend you look at the application's product documentation to figure out what exactly is wrong there. And the last thing is if you want to use NLP, then in unicast mode, we recommend you refer to this KB, because the setup is fairly detailed and it's a little difficult for us to go over this in 5 minutes. So to conclude, I would like to make a slightly broader statement than what we've been talking about here. So what we'd like to believe is that the time for virtualizing your network has arrived. So we ask all of you to join us in the vNetwork journey. And what the vNetwork distributed switch does for you as a customer is that it helps you manage your access switch at scale in a fairly efficient way through a single pane of glass. And what it does for you as a partner is it provides a rich web service integration point, as well as a switch extensibility platform to be able to build your own access switch or add value-add features around the vNetwork distributed switch. So that's all we have for today. Wei and I would be happy to take questions. There's a mic at the back, but if you guys have questions, I can take it from front as well.